Okay, so lesson 70 is about solving radical equations. And what I want you to notice right from the beginning here is that in order to be considered a radical equation, do you see that the variable is under the radical? All right, so that's an important distinction between radical equations and not radical equations. If you look over here to these, the square root of 5, for example, that is not, it's not a variable, so you could solve that one just traditionally, okay? Now, the reason that it's a big deal that you are able to determine whether it's a radical equation or a not radical equation is that radical equations, you have to always check for extraneous solutions. What in the world is an extraneous solution? It's something that is a result of squaring both sides of the equation, okay? So you don't have to check for extraneous solutions if it's a not radical equation, okay? But if it's a radical equation, that's when you have to check for extraneous solutions. And that's why it's important that you know the difference, okay? So let's talk a little bit more about what an extraneous solution is. And if you look at this sentence right here, an extraneous solution is a solution of a derived equation that is not a solution of the original equation, okay? So the idea is with extraneous solutions, you could go about your business solving this equation and come up with an answer that if you plug it back into the original, it's important that you note that it's back into the original, you literally, it wouldn't work. Okay, or it wouldn't make a true statement, even though you went through the correct processes of solving and everything, okay? So here's an example of this. If you start out x equals 5, that'd be like your original equation, right? Okay, so what's the answer for x equals 5? Well, 5, right? Okay, that's not too complicated. Now, let's do this. Let's square x equals 5. Square both sides. So you'd get x squared equals 25, right? You see that? Okay, but now when you solve for this, right? When you solve for this, you know when you take the square root of both sides, you see how you'll get x is equal to plus or minus 5, right? Now when you try plugging this back into here, do both of those create a true statement? No, no. Negative 5, so then we say negative 5 is extraneous, okay? That's the idea there, okay? What this means for you practically is that you have to check these equations, right? Because, so up to this point, I've never made you, I know back in probably middle school, they made you plug the values back into the equation and show that it works, right? Okay, I don't require that from you, maybe I should. But on these, on these radical equations, you don't have an option. In fact, if you choose not to, I can almost guarantee you that on some random test or quiz, it's going to be one of those that's extraneous and you won't be able to get any credit for it because you didn't check to see if it worked in the original, okay? That means when you get the solution, you have to go all the way back to the original and check it, all right? So let's try these here. All right, so the concept itself is very straightforward because to get rid of a radical, you can square both sides, right? So that's what we're going to do, okay? So you can square both of these, and when you square both of these, do you see that you'll get x minus 5 is equal to 14 squared, I believe, 289? 196? Okay, thank you. 196, and then when we bring the plus 5 over here, plus 5, we get x is equal to 201, right? Does everybody follow that? Okay, so now that we know that x is equal to 201, all we have to do is plug it back into the original equation. So we have 201 minus 5 equals 14. Square root of 201 minus 5. So when you take 201 minus 5 and then take the square root of it, is it a true statement? Absolutely. Okay, so this is, when I say you have to check it, this is what I mean. You can see I didn't have to show a lot of work there, okay? It's just enough to show that you actually plugged it back in and you verified that it worked, okay? And your little check mark beside it just shows me that yes, we're good, okay? Don't forget though that this is the solution. This is not the solution. This is just the proof that it works, okay? So this is the check and this is the solution. Let's try this one. Yes, Kaylee.
So on part A, the parentheses and the square root, like it takes away the square root?
It does. Remember, anytime you square something, think about like if you have square root of 2 times the square root of 2, right? That equals 2. So it's that principle that is allowing us to eliminate the radical. Very good question, yes. Okay, which actually brings up, that's a good segue into this next problem, letter B, because on B, do you see that the radical is not by itself? There's this 3 sitting here that's going to create a little bit of an issue for us. So what we need to do is get the radical by itself before we do anything else. Not hard to do, we just bring the 3 over, right? Okay, so write this down, 6x plus 7 equals 6. Okay, now we're ready for the squaring part. Okay, so when we square this, squared, squared. So now we have 6x plus 7 equals 36. Okay, you guys solve it the rest of the way, right? As soon as somebody has it, let me know what the value of x is. As I recall, it's going to be a little bit ugly. What'd you get?
X equals 29 over 6.
29 over 6. Yeah, it is a little bit ugly. 29 over 6. Noah, did you get that too? Okay, good. All right. So now we have to show the work. So when we plug it in, we put 6, and then 29 over 6, and then plus 7, plus 3 equals 9. And this actually is not as ugly as you might imagine initially, because you see how these 6's will cancel, right? So then you get 29 plus 7. What's 29 and 7?
36.
36. Okay, what's the square root of 36? 6. 6 plus 3 is equal to 9. Check, we're good. So that one, for the verification, was a little bit longer, but still not horribly cumbersome. Okay, are we good so far? Okay, so before we go to the next slide, let me remind you that because the reason squaring works is because there's this little understood 2 sitting there, right? Well, you probably know what's coming. Cube roots. Yuck, right? Okay, not impossible. They get a little uglier, but not impossible, all right? So, solving equations containing 1 cubed root. The principle is still the same, though. Do you see that we want to get rid of that negative 6? Okay, so we can do that. We have the cubed root of 4x plus 4, and that is equal to 6. So what are we going to do to both sides of this equation, people? Yeah, we're going to cube it. So, cubed, all right? 4x plus 4 equals, somebody help me out here. What's
216.
216, thank you, Brianna. All right, now, once you have the value, Alex, you have the value of x? Or anybody?
It's 53.
53? Yeah, okay, good. X equals 53, all right? Now, we're ready for checking, right? Change up the color here. Okay, so cubed root of 4 parentheses 53 plus 4 minus 6 equals 0. Okay. What's 4 times 53 plus 4? Anybody have that?
216.
216? Okay, so now we have the cubed root of 216 minus 6 equals 0. Can somebody tell me what the cubed root of 216 is? 6? Okay, which we knew, right, from a little bit ago. Okay, so 6 minus 6 equals 0. Okay, check, right? And now probably by now you're thinking, well, are there going to be any that don't work? Wait for it. There will be, okay? All right, what would you on B, is the radical by itself? No, if you don't look carefully, you'll think it's by itself. Now, I'll warn you, on your practice problems, you've got to watch out for this too. Because what if this 2 would be covered up? What if this 2 right here would be covered up? Would the radical be by itself? Not really, right? It's that negative. So when I say the radical needs to be by itself, I mean the radical must be by itself. So if there's a negative, even if there's just a negative sitting in front of the radical, divide everything by -1 before you try to start doing the squaring or cubing thing. Make sense? Okay, so let's divide everything by -2. So we can do this in our heads, right? So that gives us the cubed root of x minus 8 is equal to -7, right? Now you guys are probably ahead of me, aren't you? Did you cube everything? Careful. Do you see how I put parentheses around this -7 and then cubed it? That is an important idea because it's the whole thing. Whatever that is, the whole thing cubed. So then I get x minus 8 is equal to, somebody have that?
-343.
Thank you, -343. And do you see how that became negative? because we knew that it was the whole thing cubed, right? All of that, -7 was cubed. All right, does somebody have a value for x?
Negative 335.
-3 what, 35? Okay, -335. Okay, now we're ready to plug it back into the original. Let me change the color. -2 cubed root of -335, -335 minus 8 equals 14. Okay, well, let's just take care of the cubed root stuff. That, we already know it's -7, don't we? Right? Does everybody see that? Okay, so all of this part right here is equal to -7. So we have -2 times -7 equals 14. Well, yes, it does. We're good. Okay? Do you see now why back when we were talking about cubed roots of negative values, they've been testing you over the course of time. Do you know that you can take the cubed root of a negative value? Yes, you can get -7. Some of you, if you're not on your A game, will try to, you'll see this negative under the radical, this -343 right here, and you'll try to make it 343i. Why can you not do that? Why can you not do that? There's a very specific reason. Because it's cubed, right? I is especially for square roots or fourth roots or even roots, right? Remember the other day when we did the patterns with I? There was no odd roots, or there was no odd powers, okay? So don't be trying to use I with odd indices. That's the plural for index, okay? This is an odd, 3 is an odd index. Good so far? Okay.